This tiny ring costs pennies, holds bearings securely in place, and can also weaken the shaft if it's used incorrectly. Today we'll see why both cases are true. Welcome back to the component file, where we break down one mechanical component at a time. Last episode was the knurled thumb nut with side holes. Today we are looking at the retaining ring. Hi everyone, if you're new here, my name is Jamal. I'm a mechanical design engineer with over 8 years of experience designing machines for automotive, aerospace, and industrial automation. If you are interested in machine design, SolidWorks, or preparing for a CSWA or CSWP exam, you are in the right place. So, what is a retaining ring? It's also called a circlip. It is a spring steel ring that snaps in a groove on a shaft or inside more. It acts as a removable shoulder, holding bearing, rings, pulleys, and other components in position without threads or weld features. Why it exists? So instead of machining permanent shoulders on a shaft, that of course will raise the cost of either a shaft or a bore, a retaining ring provides a small axial stop using only a small groove. So instead of adding material, you remove material, you clear the place for the ring, you place it there, and it actually does the job of a welded or a machined shoulder. It's cheaper, saves space, and can easily be removed during maintenance. So the way it works is that the ring expands or compresses during installation, then springs back into the groove. Once seated, it resists axial movement while remaining easy to remove with retaining ring pillar. So basically the pillars are the two tools that we use to remove this kind of rings. Where we use them, so you can actually find them in a handful of components or mechanical assemblies. So mainly in bearing assemblies, gearbox, hydraulic cylinders, electrical motors, automotive transmission, industrial automation equipment generally. Before we move on to the design, I would like to remind you that choosing the right retaining ring isn't enough. You also need the correct groove dimension and clearance. That's exactly what we cover in Machine Design Verification Toolkit. You can download it using the link below. Back to the design. So when it comes to designing this kind of rings, to be honest, most of the time you would never need to design it by yourself because you can just pick it up from a catalog from Izumi or knurled. But for the sake of SolidWorks tutorial, let's just go ahead and design it. But what I advise you to do is to focus more on the integration side of design. So when you want to design the shaft where the ring's gonna go, you have to focus on the correct groove diameter, correct groove width and depth, and proper groove location. So that's what would matter when it comes to actually designing one that goes inside your assembly. Let's jump into designing the first C-shape circlip. So basically to design the C-shape circlips or retaining ring, you just need one sketch. So basically just one step design, easy, straightforward, but of course, let's see what we can learn from this design. So basically, that's actually the sketch that we have used. What I advise you to do is just to stop the video right here, take a screenshot and go ahead and design it by yourself, or try to actually draft it by yourself and then come back here to see how we are going to do it together. Without further ado, let's jump into it. So to create this kind of parts, just go to new, click on new, and then click on parts and then click on OK. So once you're here, just choose the front face. Let's make the background white. I like making it white all the time. Just choose the front plane, sketch, and then start sketching. So basically you draw the first circle and then the second circle, right? Like that. So basically the internal diameter should be 9.3. So basically these are dimensions that I got from the catalog. I'm not making up anything from my mind. So if you checked Mizumi's catalog or knurled's catalog, you can just find the same dimension. If you are interested in knowing where did I get these from. So the distance between this one and this one is actually 0.5. Perfect, we are done with that. Let's just this one and this one like that. There we go. So once you get a defined sketch, just go ahead and create a center line here. And let's actually create the kind of ears, if you want to call them that. Well, they look like ears. So and then this one here, and then you go here, and then you just do that. Voila, so our ears are taking shape. Let's add the internal or the tools hole here. So this distance should be 2.5. There we have it. And then this radius right here should be 1 mm. And then this hole right here should be 1.2. Yep, definitely we need to add dimension here as well. So it's 2 mm. Voila, our design is taking shape. Let's add another dimension here. So it's 1.5 mm. There we have it. Let's just make it tangent to this one. Voila. We are done with that. Let's actually locate this one. To do that, we should just add this dimension right here. So it's 0.5. And voila, you will get your sketch fully black. And of course, that is our target, is making our sketch fully black. So once you're done with that, just go ahead and delete these 2 lines. And to actually draw the other side, we don't need to actually go through the burden of drawing them all. Just select these couple of sketches. And the mirroring about is this center line that we have created earlier. And let's go and trim some entities. And voila, so now you got your C-shaped circlips. Let's go ahead and extrude it. So it's extruded by 1 mm. And let's go ahead and apply material. So most of the time you will find these rings made out of stainless steel, carbon steel as well, with the black oxide. So if you're going to use it in automotive industry, or if you're going to use it, of course, in pharmaceutical industry, food industry, you should use a stainless steel and focus on the grade of the steel. So most of the time you use 316. And voila, that's our design is done. What I would advise you to do is actually to create it by yourself. And of course, you can go ahead and try and create the second one. Let's just go ahead and open it up so you can see the dimensions if you want to create them by yourself. Let's edit. And here it is. You can just stop the video here and try to actually get all the dimensions together and then go ahead and do it by yourself. That sums up the design side of it. Let's now look at the common mistakes that engineers make during the integration or in the implementation of these kind of rings. So the biggest mistake is cutting the groove to a rough, close enough dimension instead of exact catalog spec. So what I advise you to do is just go ahead and implement the exact catalog spec without trying to make up the numbers from your head, because then you'd be wondering why the ring's rated capacity does not match the reality. It's because you didn't really apply the exact catalog specs. So second is placing the groove right at the shaft highest bending stress point, purely for convenience, stacking a stress concentration exactly where the shaft can least afford one. A retainer ring is one of the simplest components in a machine design, but only when it's installed in the right groove, in the right location. So next episode, we'll be discussing the hairpin. Of course, I'm not talking about the gun's hairpin. I'm talking about the mechanical hairpin. If you enjoyed this episode, make sure to subscribe for more practical machine design content. And don't forget to download the machine design verification toolkit by using the link down below. Again, thanks for watching and see you in the next